Hi everybody, so we're in section 8.3 talking about applications to physics and engineering, so our applications for integration. So the main thing that we're going to be talking about in this section is the concept of a centroid, centroid meaning a center of mass for a particular region. So consider a plate of any given shape being balanced horizontally. The point P on which it balances is called the center of mass, or center of gravity. We say this plate occupies a region R of the plane between A and B, above the x-axis, and beneath the curve f of x, and the center of mass of this region is the centroid of R. This centroid is located at the point x bar, y bar, where x bar is 1 over a times the integral from a to b of x f of x dx, and y bar is 1 over a times the integral from a to b of 1/2 f of x squared dx. And this is where A is the area of R. So that region that we're looking at. Okay, so basically what we're having here is, do a different color. I have some plate of random shape being balanced on a single point, P. That place where it balances horizontally, that is the centroid. Okay, that is its center of mass or center of gravity. So oftentimes we define these shapes to be above the x-axis, going from a to b, and under the function f of x. So we have our region R. Okay, so this is our region R. And then wherever that point is, that center of gravity, that center of mass, that would be P, our centroid. Okay, and that centroid is the point x bar, y bar. Okay, and we just came up with formulas to be able to identify where this centroid occurs. All right, so let's look at this example. Find the center of mass of a semicircular plate of radius r. All right, so we can go ahead and place the semicircle above the x-axis. So we're going to place semicircle. Oops. So we're going to place the semicircle such that I'm going to pick it so that it's centered around the origin, because of course that's going to make our calculations so much easier. So such that f of x is the top half of that circle, so that's r squared, square root of r squared minus x squared, with a being negative r and b being positive r. So basically we're going from negative r to r, okay, that's also r. And there's the top half of our circle, sort of. Okay, so that's our region in question, is that semicircle. Okay. Now, in order to find the center of mass, or the centroid of this, we need to identify x bar and y bar, but there is one principle that's actually going to help simplify our work here a little bit. So, and that one we haven't talked about yet, and that is the symmetry principle. So the symmetry principle tells us, since the region R is symmetric about the y-axis, and really it could be symmetric about any line, but in this case it's the y-axis, the centroid must lie on this line. So the symmetry principle tells us that if the region is symmetric, the centroid must lie on that line of symmetry. Okay, so what this tells us, we don't need to find x bar because we know that since it has symmetry about the y-axis here, the centroid has to lie on that line somewhere. So we don't need to find x bar. We know it must be equal to 0 because it has to lie on that y-axis due to the symmetry. Now, you could go ahead and actually find it, right? If you wanted to calculate x bar yourself, you would just find that it gives you 0. So that would be kind of a fruitless search, but it is possible to find it. Okay. So we do need to find, however, the value of y bar. So to find y bar, we need A. So the area our area A. The area of the semicircle, right, it would be just half the area of a circle. So it's 1/2 pi r squared. Okay. So thus, let's go ahead and find y bar. So y bar equals 1 over A, so 1 over 1/2 pi r squared, times the integral from negative r to r of 1/2 f of x, so that's r square root of r squared minus x squared squared dx. Okay. So we can pull that 1/2 out, and this 1/2 here is going to cancel with this 1/2 here, because you have one in the top, one in the bottom. So we're just left with 1 over pi r squared, integral negative r to r of r squared minus x squared dx. Okay. Take the antiderivative. This is with respect to x. So we get 1 over pi r squared times r squared x minus 1/3 x cubed, evaluated from negative r to r. And then if we evaluate that, we get 4r over 3 pi. All right, so what that tells us, so the center is over here, the center of mass is at the point 0, 4r over 3 pi. And this is in terms of r, because we don't know what r is, right? So what this means is that for any semicircular plate of radius r, if we know what the radius is, we can find that center of mass. It will always be at 0, something, and that output value, that y value, can be determined depending on how big the semicircle is, right? The bigger the semicircle, the higher that center of mass is going to be. All right. Let's look at another example. Find the centroid of the region bounded by the curves y equals cosine of x, y equals 0, x equals 0, and x equals pi over 2. So for this one, let me just draw the region here really quickly. So we have our cosine function from 0 to pi over 2. So this is the region in question. Right, that's y equals cosine of x. So the area, because we're going to need that in order to find the centroid, so the area, that's going to be, right, the integral under the cosine curve from 0 to pi over 2 under cosine x dx. So that's just going to be sine of x evaluated from 0 to pi over 2. That's going to be 1 minus 0, which is just 1. Okay, so the area of the region is just 1. Okay, so let's keep that off to the side here. So now we're going to find x bar and y bar. So x bar, that's going to be 1 over a, integral from a to b, so just say from 0 to pi over 2 of x f of x dx. Okay, so area is 1, so that's just 1 over 1, so that just disappears. That's integral 0 to pi over 2 of x cosine of x dx. Now this one, we do need integration by parts for this. So let me just kind of write this over off to the side here. So we're going to go ahead and let u be x. Then du is just 1, right, dx. dv is going to be cosine x dx. And v is going to be sine of x. So if we do that, then we get x sine x evaluated from 0 to pi over 2 minus the integral from 0 to pi over 2 of just sine of x dx. Now if we evaluate these, so evaluate x sine x from pi over 2 minus 0, and then evaluate the integral, what you end up getting here is just pi over 2 minus 1. So this is the value that we get. So let me just separate this here. So we get pi over 2 minus 1 as our x bar value. So then the y bar value, that's going to be, right, 1 over a integral from 0 to pi over 2 of 1/2 f of x squared dx. So for this one, a is still 1, right? So let's get the 1/2 out of there. Integral 0 to pi over 2 of cosine squared x dx. Now for this one, we can't really use trig identity here because taking the integral of cosine squared, just turning it into 1 minus sine squared, you haven't fixed the problem. You just have sines instead of cosines. So we're going to use here that double angle identity that we saw back in chapter 7. So that identity says, so I have 1/2 integral 0 pi over 2. That tells us cosine squared of x is going to be 1/2 times 1 plus cosine of 2x dx. Okay, 1/2 and 1/2 is 1/4. Antiderivative of 1 plus cosine 2x is x plus 1/2 sine of 2x. Evaluated from 0 to pi over 2. Okay. And then if you evaluate this, right, so evaluate f of b minus f of a, multiply by the 1/4, you end up getting pi over 8 for this value. Okay. So the centroid whoa, I cannot write, centroid is the point pi over 2 minus 1, comma, pi over 8. And that would be our center of mass for this region. Okay, so if we go back onto the original graph here, pi over 2 minus 1, so that's going to be somewhere around here, and then comma pi over 8, so that's going to be, right, if this is 1, then pi over 8, that's going to be somewhere, so like somewhere in here, roughly, right, which should make sense. That's where, right, it's not too far to any of the outskirts, a lot of the mass is right there in the middle. So that's the value that we get for the centroid by calculating x bar and y bar. Now, if the region R lies between two curves, right, f of x and g of x, where f is greater than or equal to g, then the centroid can be found using the following formulas. So it's going to be very similar, just with a slight modification for the area between two curves. So 1 over a, integral from a to b, of x times f of x minus g of x dx, and y bar is going to be 1 over a times the integral from a to b of 1/2 f of x squared minus g of x squared dx. Okay, so it's in essence the same formula, just now with the subtraction, the difference between the two functions in there. Okay, so let's take a look at an example that utilizes these values for the centroid. So the centroid of the region bounded by the line y equals x and the parabola y equals x squared. So the region, do this up here, so there's our parabola, there's our line. So from, there's 1, 1, 0. So that's the region in question. So we need top function and bottom function. So in this case, we're going to take the top function as the line. So take f of x is x, g of x, that bottom function is x squared. And then a and b are determined by those intersection points. So a is 0, b is 1. So for the area of the region, let's get that first. The area, that's going to be the integral from 0 to 1 of x minus x squared dx. Okay, so that's going to be x squared over 2 minus x cubed over 3 from 0 to 1. Evaluate that, gives us 1/6. Okay, so our area is 1/6. So let's go ahead and find x bar and y bar. So x bar, that's going to be 1 over a, so 1 over 1/6 times the integral from 0 to 1 of x times x minus x squared dx, right? F of x minus g of x. So that's going to be 6 times integral 0 to 1 of x squared minus x cubed dx. So we get 6 times x cubed over 3 minus x to the, x to the fourth over 4, evaluated from 0 to 1, okay, which ends up just giving us 1/2. And then y bar, so that's 1 over 1/6, integral from 0 to 1 of 1/2 times x squared minus x squared squared dx. So that's going to be 6 times the integral 0 to 1. Actually, we'll just multiply the 6 and the 1/2 right now. So that's going to just be 3. X squared minus x to the fourth dx. So that's 3 times x cubed over 3 minus x to the fifth over 5. Evaluated from 0 to 1. And that evaluation gives us 2/5. So we get our centroid. So the centroid is at the point 1/2, 2/5. Okay, and you can look on the original graph too and see, so 1/2, divide this 1, 2, 3, 4, 5, 2/5. It's going to be right about here, roughly. So that's where our centroid would lie for this region. All right. So that's the end of 8.3. So now let's go ahead and move into 8.4. So again, looking at further application, but this time to economics and biology. So a little bit of everything here in this section. So the first thing that we're going to look at for the economics side of things, we're going to talk a little bit about the demand curve. So the demand curve for a product defines a relationship between price per unit and quantity demanded by consumers. The point, big X, big P, is the point where the product is currently selling X units for P dollars. So our demand curve, so our x-axis and our p-axis, so our demand curve is going to look something like this. So it has a downward relationship. It's an inverse relationship because as the price goes down, demand goes up, and as price goes up, demand goes down. So this is our function p of x. Okay, there's our origin, and then this point right here, which is arbitrary, this point will be the point x, p. Okay, there's our x coordinate, our p coordinate. Okay, so that point is just whatever they're currently selling at, right? That many units for that price. At this current price, many consumers would be willing to pay more, right? So, if I'm currently paying, for like a candy bar, if I'm currently paying $1 for a candy bar, I would be willing to probably pay, $1.50 for a candy bar. So, at the current price, many consumers would be willing to pay somewhat more. The amount of money that they are saving by paying the current price instead of the price they would be willing to pay is called consumer surplus. So consumer surplus. Okay, so in my candy bar example, I would be willing to pay up to $1.50 for a candy bar. I'm only paying $1 right now. So that means that I have saved 50 cents. Right? 50 cents that I would have been willing to pay, but I didn't have to because of the current price. Okay? when we're trying to find and compute what consumer surplus is, we're going to be using the following formula. So consumer surplus, that is the integral from 0 to x of p of x minus p dx. Okay, so here's our curve. Here's our point x comma p. Okay. And again, this is our function p of x. What this is telling us is the amount of money that they are willing to spend is the entire area underneath the demand curve. Okay? The entire area underneath the demand curve. But what they're currently paying is just at the value of p. So that's right here. So that's p. That's what they're currently paying. Okay? But they would be willing to pay all of these prices up here. Okay? So what we're doing here is we're taking the total area. This is the total amount they would be willing to pay minus the amount that they are currently paying. That result, again, is the consumer surplus. That's this value up here. Okay, so the amount that they would be willing to pay minus the amount they are currently paying, and then find that area. And that's going to give us the consumer surplus. Okay, so again, the value in here, that's our consumer surplus. Okay. So computing this is just computing an integral. So let's look at this example. The demand for a product in dollars is P equals 1200 minus 0.2x minus 0.0001x squared. Find consumer surplus when the sales level is 500. Okay, so first off, when the sales level is 500, so when x equals 500, the price is going to be 1200 minus 0.2 times 500 minus 0.0001 times 500 squared, which is 1075. Okay. So our consumer surplus is the integral from 0 to 500 of the function 1200 minus 0.2x minus 0.0001 x squared minus 1075 dx. Okay. And then this integral, this is just a standard, right, undoing the power rule, so I'm going to leave that to you as an exercise, but what we get is the value in dollars, $33,333.33. Okay, so that's how much money the consumers would be saving at this current price of 1075 compared to what they would be willing to pay for this product. Okay, so that is our consumer surplus. All right. So now let's look at the biology side of things here. So for this first example, we have the cardiac output of the heart gives the volume of blood pumped by the heart per unit time. So that should be per unit time. So just get rid of that. So per unit time, we can measure this by injecting dye into the heart and measuring the concentration of it leaving the heart. cardiac output is given by this formula, so it's F equals A over the integral from 0 to t of C of t dt. This is where A is the amount of dye that's administered, C of t is the concentration of the dye at time t. Okay, so if we know the amount of dye and we know the concentration at any given time, we can then find the output, the cardiac output of this heart. Okay, so let's look at an example. A 5 milligram bolus of dye is injected into a right atrium. The concentration of the dye in milligrams per liter is measured in the aorta at 1 second intervals as shown in the table. Estimate the cardiac output. So in this case, we don't have a function per se, we just have values over intervals, but that's okay because that's really more accurate, right? For when we're dealing with real data, rather than having a function, we just have approximate values over time. So here, here we go. So here, A, the amount of dye, is 5, and we can't evaluate exactly because we don't have that function C of t. So what we're going to do is we will approximate. We're going to approximate the value of that integral using one of our approximate integration techniques. And this is precisely why we have those approximate integration techniques, because of situations where we don't know the exact function. So we will approximate using the best one that we have is Simpson's rule. So a little bit of a blast from the past here. So Simpson's rule with delta t equals 1. So the change in time over the intervals is 1. That's our width, right, of each rectangle or each polygon. And big T equals 10. Right? So that's our number of subintervals. So the integral from 0 to 10 of C of t dt will be approximately equal to 1/3 times, so now we're going with these outputs here. These are the ones that we're using. So 0 plus 4 times 0.4 plus 2 times 2.8 plus 4 times 6.5. So remember this pattern, right? It goes 1 and then 4, 2, 4, 2, 4, 2 all the way down until we get to the very end. So plus 2 times 9.8 plus 4 times 8.9 plus 2 times 6.1 plus 4 times 4.0 plus 2 times 2.3 plus 4 times 1.1 plus 0. So those are our values for approximation. Notice just an interesting thing about the relationship of the numbers here. The concentration itself is behaving as you might expect, right? It's starting at 0 because it's not in there yet. It starts increasing, right? The amount of dye being pumped through is getting larger. And then at some point, it starts getting lower again, right? The concentration is starting to diffuse a bit into the bloodstream until eventually there is none left. Okay. So this value, this numerical value that we get is, if you run that calculation, is approximately 41.87. So, say thus, cardiac output is f equals, so a over the integral from 0 to 10 of c of t dt. That will be approximately equal to 5 over 41.87, which is approximately 0.12 liters per second. So then extrapolating that into minutes, our standard units, so 7.2 liters per minute.